Lesson 9.1, Inference from Two Proportions. Chapter 8 was largely inferences from one proportion, or one mean, or one variance. But here we're comparing two proportions from different populations. So the key idea will be testing one stat against another. But before we dive in too deep, a few new subscripts. Because we have two different proportions, we need to distinguish some of our variables. So you will notice that some of these have like a little subscript on them. Yeah? So these are all from population 1. And then likewise, the same goes for population 2. Now, we also need to, what's said is pool our two samples together, which means we're just going to combine them. And we do that by adding our successes and then our trials. And that creates P bar and Q bar, our success proportion and our failure proportion. We will need requirements for these tests to work. We need to have simple random sampling, and the two samples that we look at should be independent of each other. And finally, for each sample, the counts must be greater than 10, or as they say, n times p hat and q times p hat must be greater than or equal to 5. All right? Test statistics. So this is how we calculate our z-stat, which tells us where in the normal population we are, using, you see, two proportions there, yeah? And then we subtract the actual proportions. Now this is going to be assumed to be 0, because we're going to do a hypothesis test here, and we will assume that P1 equals P2. And then we have our pooled samples in our denominator. And anyways, that gives us Z. We will also find the confidence interval. Notice we have the two errors. We're subtracting the error and adding the error. And then this would represent P1 minus P2. And there's how we calculate the error, with our z alpha over 2 and then the square root of those two. Now both this error stat and the z-stat can be found using number crunch in any, whether on your calculator, whether you're doing it there too. So this is considered a 2-sample z-stat. So look for it there. Important note. When we do the hypothesis testing, the null case will always be P1 equals to P2. So then our alternative case will be when they don't equal each other. So the one big example here is license plates. Somehow in Connecticut, the laws are a little bit stricter with those who have rear license plates than opposed to New York. Well, sorry, New York is more strict license, whereas Connecticut's a little bit loose. More people get away. So the author does a survey and to see if laws are being enforced differently in both states, or again, are they the same? The success is defined, first of all, as plates in the rear only. So you can see here 239 over the population 1 and over sample 1, and our 9 over the sample 2. We have all 3 requirements met. That is, the samples are independent of each other. It's a simple random survey. We trust the author to have done this properly. And then n times p much larger than 5. All right, and the claim that both states, New York and Connecticut, have the same ratio. So notice we set P1 equal to P2. And here's our pooled success and our pooled failure rate, 90%. So using the 5% significance level, again, when I subtract P1 minus P2, again, the assumption is that they're the same. And so our z-stat gives us 7.11, rounded to the nearest hundredth. Okay. If you then take this z-stat to a table, it will report, it'll actually report 0.0001, but you multiply that by 2 since it's a two-tail statistic, and we get 0.002. Using technology, however, we get something a little bit more accurate. It's much closer to 0. And so when you do your technology StatCrunch, you will get a p-value of 0.000. So because this is less than our tolerance, we reject H sub 0, right? We are in that zone of 2 standard deviations or more, so this was not chance. There is sufficient evidence to conclude that Connecticut and New York have different proportions of cars with plates in the rear only. So it's reasonable to conclude enforcement is different in each state. Otherwise, people wouldn't do that, right? And here are 2 different graphs. The first one shows the p-value. The second one shows the critical value method. And we can see we are well in that zone. And if you're in the critical value, you take alpha. This is your tolerance, right? And we find the corresponding z-value. And since that is larger than that, we are, again, to the right of that region. So, yeah, we reject. Now, looking at confidence intervals. The trick here is, does the confidence interval include 0? If it does, then P1 equals P2, or it could be. So that at that point, we would not be able to reject. So finding the error, again, using that formula above, we get 0.017482, about 1.7%. I take my p hat minus my p hat of the 2 populations. I get about 10%. Okay, and then I subtract the error and I add the error. And notice here we have between 8% and 11% is the difference between the real population difference. So we can safely conclude with 95% confidence that the interval does not include 0. And so the 2 population proportions are not equal. So again, that backs up what we came up with earlier. Hope that all makes sense to you. Good luck in doing your only section from Chapter 9.